Ground overcurrent in a power distribution unit, or PDU, can be a complex issue, often stemming from a variety of factors. Effective troubleshooting involves a systematic approach to identify and mitigate the root cause. Firstly, verify load balancing on single-phase circuits. The amperage on the neutral conductor should ideally match the amperage in the hot phase conductor. A significant difference suggests a leakage to ground, which directly contributes to ground overcurrent. Use an ammeter to measure the current on both the hot and neutral conductors of each single-phase circuit. Significant discrepancies should be investigated further. Secondly, inspect the grounding system. A properly bonded grounded conductor to the grounding electrode system is crucial. Check the neutral grounding point for loose connections or damaged equipment. Ensure the grounding electrode conductor is appropriately sized according to the 2017 National Electrical Code, or NEC, Table 250.66, and that it is securely connected to the grounding electrode. A loose or corroded connection can impede the flow of fault current, leading to elevated ground overcurrent readings. Thirdly, check for harmonic content. Excessive harmonics on neutral conductors can indeed cause ground overcurrent. Harmonics are multiples of the fundamental frequency of the power system, typically 60 Hz in the United States. Nonlinear loads, such as electronic devices, can generate harmonic currents that accumulate on the neutral conductor, potentially exceeding its capacity and causing ground overcurrent. Use a power quality analyzer to measure harmonic levels, particularly the third, fifth, and seventh harmonics. Identify potential sources of harmonic distortion, such as variable frequency drives, electronic ballast, and uninterruptible power supplies. Fourthly, investigate inductance. Inductance in metal-clad, or MC, cables can induce voltage and currents in the grounding conductor, which then leads to ground overcurrent. When MC cables are routed near higher voltage conductors, inductive coupling can occur, causing current to flow through the grounding conductor. Ensure MC cables are not routed in close proximity to high voltage conductors, particularly those operating at 277/480 volts. Maintain adequate separation between MC cables and high voltage conductors to minimize inductive coupling. Fifthly, review installation practices. Proper grounding and bonding practices during installation are essential for preventing ground overcurrent. Verify that all equipment is properly grounded and that no ground loops exist. A ground loop occurs when multiple ground paths exist between two pieces of equipment, creating a circulating current that can contribute to ground overcurrent. Ensure that each piece of equipment has a single, direct connection to the grounding electrode system. Sixthly, eliminate leaking equipment. Ground insulation faults in equipment can cause current to leak to ground, leading to ground overcurrent. Use an insulation tester, also known as a megometer, to identify equipment with ground insulation faults. Disconnect and isolate any faulty equipment to determine if the ground overcurrent issue is resolved. A common test voltage for 120/208 volt circuits is 500 volts DC. Seventhly, consider the LCD televisions as a source. Although the television manufacturer denies responsibility, the consistently increasing ground overcurrent with the installation of more LCD televisions may be related to their power supplies. Modern electronic devices often use switching mode power supplies, which can generate harmonic currents and contribute to ground overcurrent. Conduct further testing to determine if the televisions contribute to the ground overcurrent issue. Measure the ground current with the televisions connected and disconnected to quantify their impact. Eighthly, trace and isolate ground overcurrent. Identify the problem circuits by tracing ground overcurrent from the PDU load center to the affected sub-panel. Use a clamp-on ammeter to measure the current on the grounding conductors of each circuit. Disconnect and isolate affected circuits until the ground overcurrent is eliminated. This process helps pinpoint the specific circuit or piece of equipment causing the issue. Ninthly, implement mitigation measures. Once the source of ground overcurrent is identified, implement appropriate mitigation measures. Mitigation measures include installing harmonic filters, rerouting MC cables, improving grounding practices, and replacing faulty equipment. Harmonic filters can reduce the levels of harmonic currents on the neutral conductor, minimizing ground overcurrent. Rerouting MC cables can reduce inductive coupling and prevent current from flowing through the grounding conductor. Improving grounding practices can ensure that all equipment is properly grounded and that no ground loops exist. Replacing faulty equipment can eliminate ground insulation faults and prevent current from leaking to ground. Ground overcurrent is typically defined as the current exceeding the ampacity of the grounded neutral conductor, or an unintended current flowing through the grounding path. Here's a deeper dive into potential causes and solutions. Firstly, unbalanced loads. In a three-phase system, if the phase loads are not balanced, current will flow on the neutral conductor. The neutral current can be calculated as the vector sum of the phase currents. If the neutral current exceeds the conductor's ampacity, it can trigger a ground overcurrent alarm. Ensure loads are distributed as evenly as possible across all three phases to minimize neutral current. Secondly, harmonic currents. As mentioned earlier, nonlinear loads such as variable frequency drives, computers, and LED lighting can generate harmonic currents. These currents, especially the third harmonic and its multiples, act directly on the neutral conductor in a three-phase four-wire system. Install harmonic filters to mitigate harmonic currents, or use equipment designed to minimize harmonic generation. Thirdly, neutral to ground faults. A fault between the neutral and ground conductors can cause current to flow through the grounding path, leading to ground overcurrent. Inspect wiring and connections for any signs of insulation damage or accidental contact between neutral and ground conductors. Use an insulation resistance tester to check for insulation breakdown. Fourthly, multiple neutral to ground bonds. In a properly grounded system, the neutral conductor should only be bonded to ground at the service entrance or the separately derived system. Multiple neutral to ground bonds can create parallel paths for neutral current, causing current to flow through the grounding path. Identify and eliminate any unintended neutral to ground bonds. Fifthly, ground loops. Ground loops can occur when there are multiple paths to ground, creating a loop through which current can circulate. This circulating current can contribute to ground overcurrent. Ensure that each piece of equipment has a single, direct connection to the grounding electrode system. Avoid creating multiple ground paths. Sixthly, faulty equipment. Defective equipment with insulation breakdown can leak current to ground, causing ground overcurrent. Use an insulation resistance tester to check the insulation resistance of equipment. Replace or repair any faulty equipment. Seventhly, improper grounding electrode system. An inadequate grounding electrode system can limit the ability of the system to safely handle fault currents, leading to ground overcurrent. Ensure that the grounding electrode system meets the requirements of the 2017 NEC, specifically Article 250. This may involve installing additional grounding electrodes or improving the conductivity of existing electrodes. Eighthly, electromagnetic interference, or EMI. EMI can induce currents in the grounding conductors, contributing to ground overcurrent. Use shielded cables and proper grounding techniques to minimize EMI. Separate power and signal cables to reduce inductive coupling. Ninthly, capacitive coupling. Capacitive coupling between conductors can cause current to flow through the grounding path, particularly in long cable runs. Use shielded cables and reduce the length of parallel cable runs to minimize capacitive coupling. Tenthly, transient voltages. Transient voltages, such as those caused by lightning strikes or switching surges, can cause current to flow through the grounding path, leading to ground overcurrent. Install surge protective devices, or SPDs, to protect equipment from transient voltages. Now, let's discuss specific steps for troubleshooting ground overcurrent in the provided scenario. Firstly, verify the accuracy of the PDU monitor. Use a calibrated clamp-on ammeter to independently measure the ground current at the PDU neutral busbar. Compare this reading to the PDU monitor reading. If there is a significant discrepancy, the PDU monitor may be faulty and need to be recalibrated or replaced. Secondly, isolate the sub-panel. Disconnect the 100 amp breaker feeding the sub-panel from the PDU load center. Monitor the ground current at the PDU neutral busbar. If the ground current drops significantly, the issue is likely within the subpanel or its connected loads. Thirdly, measure ground current at the subpanel. With the subpanel disconnected from the PDU, measure the ground current on the grounding conductor at the subpanel. If there is significant ground current, the issue is within the subpanel or its connected loads. Fourthly, disconnect branch circuits. One by one, disconnect the branch circuits feeding the LCD televisions at the subpanel. After disconnecting each circuit, measure the ground current at the subpanel. If the ground current drops significantly when a particular circuit is disconnected, that circuit is likely the source of the ground overcurrent. Fifthly, inspect the wiring of the affected circuit. Carefully inspect the wiring of the affected circuit for any signs of insulation damage, loose connections, or improper grounding. Pay close attention to the connections at the receptacles and the LCD televisions. Sixthly, test the LCD televisions. Disconnect the LCD televisions from the affected circuit and test them individually. Use an insulation resistance tester to check for insulation breakdown between the power cord conductors and the television chassis. Seventhly, check the neutral to ground bond at the subpanel. Verify that the neutral conductor is properly bonded to the grounding electrode system at the subpanel. Ensure that there are no unintended neutral to ground bonds. Eighthly, inspect the MC cable routing. Check the routing of the MC cable feeding the subpanel. Ensure that it is not routed in close proximity to high voltage conductors. Maintain adequate separation to minimize inductive coupling. Ninthly, consider using a ground fault circuit interrupter or GFCI breaker. Replace the standard breaker feeding the affected circuit with a GFCI breaker. A GFCI breaker will trip if it detects a ground fault, providing additional protection. Tenthly, consult with a qualified electrician. If you are unable to identify and resolve the ground overcurrent issue, consult with a qualified electrician experienced in troubleshooting power distribution systems. Furthermore, consider the specific equipment being used. Firstly, LCD televisions. The fact that the ground overcurrent increases as more LCD televisions are added strongly suggests that they are contributing to the problem. While the manufacturer may deny responsibility, it is important to investigate further. The switching power supplies in these televisions are known to generate harmonic currents which can contribute to neutral current and ground overcurrent. Try using a power quality analyzer to measure the harmonic content of the current drawn by the televisions. Secondly, MC cable. While MC cable is generally a safe and reliable wiring method, it can be susceptible to inductive coupling, especially when run in close proximity to high voltage conductors. The inductance of the MC cable can induce voltage and currents in the grounding conductor, leading to ground overcurrent. Ensure that the MC cable is properly grounded at both ends to minimize inductive coupling. Thirdly, the PDU itself. The PDU is a separately derived system, which means that it has its own grounding electrode system that is independent of the building's grounding electrode system. It is critical to ensure that the PDU is properly grounded in accordance with the 2017 NEC. Check the size of the grounding electrode conductor, the grounding electrodes, and the connections to the grounding electrodes. Fourthly, subpanel. The subpanel is fed by a three-phase 4-wire circuit, which means that it has a neutral conductor in addition to the three-phase conductors and the grounding conductor. It is important to ensure that the neutral conductor is properly sized and that it is not overloaded. An overloaded neutral conductor can contribute to ground overcurrent. Now let's address the specific questions posed. Could this ground overcurrent be caused by harmonics on the neutrals of the circuits? Yes, harmonics are a very likely cause. Nonlinear loads such as the LCD televisions generate harmonic currents which add directly on the neutral conductor. These harmonic currents can overload the neutral conductor and contribute to ground overcurrent. Could this be caused by inductance of the MC cables in close proximity of a higher voltage of 277/480 volts alternating current? Yes, inductance is another possible cause. When MC cables are run in close proximity to high voltage conductors, inductive coupling can occur, inducing voltage and currents in the grounding conductor. This induced current can contribute to ground overcurrent. Could there be other grounding issues not addressed upon the initial installation process? Yes, improper grounding is always a possibility. Verify that all equipment is properly grounded, that there are no unintended neutral to ground bonds, and that the grounding electrode system is adequate. Finally, regarding approaching the problem, here's a summary. Firstly, verify the PDU monitor accuracy. Secondly, isolate the subpanel. Thirdly, measure the ground current at the subpanel. Fourthly, disconnect the branch circuits one by one. Fifthly, inspect the wiring of the affected circuits. Sixthly, test the LCD televisions individually. Seventhly, check the neutral to ground bond at the subpanel. Eighthly, inspect the MC cable routing. Ninthly, consider using a GFCI breaker. Tenthly, consult with a qualified electrician. By following a systematic approach and carefully investigating each potential cause, you should be able to identify and resolve the ground overcurrent issue in the PDU system. Remember to always prioritize safety when working with electrical systems. If you are not comfortable working with electricity, consult with a qualified electrician. Always de-energize circuits before working on them and use appropriate personal protective equipment, or PPE.